we present an optical flow approach named adaptive graph reasoning. Optical flow is a fundamental task in video understanding and analysis, aiming to estimate the pixel-wise correspondence between two video frames. Current methods largely focus on addressing the matching similarity with four-dimensional cost volumes, lacking a holistic motion understanding of the given scene. First, we present the motivation of this work. Here we show a challenging image pair with heavy motion blur from the final pass of Syntel test set. As we can see, previous state-of-the-art methods, RAFT and SCV, suffer from ambiguous matching. Let's consider the reason why holistic motion understanding is far from being achieved. First, existing approaches capture scene information with only naive operations, without typed functions for explicitly modeling such process. Second, their operations are confined to the original coordinate space with local operations, lacking a global understanding of the given scene. Third, they ignore the adverse effect caused by domain gap, the gap between scene content and motion features. To tackle these issues, we introduce a novel graph-based approach, namely adaptive graph reasoning for optical flow, which embeds graph techniques onto the matching pipeline to enable an effective context reasoning and information interaction. Unlike previous approaches simply employing concatenation operation on context and motion feature, we develop a task-specific graph reasoning approach that can fully exploit scene context to effectively assist motion estimation with shape and region constraints. Now we introduce the proposed adaptive graph reasoning flow network in detail. The first step is to project context and motion features in regular coordinate space into graph space. The project operation decouples positional information from the original grid feature, and makes the produced low-dimensional node feature representations more compact and with sufficient expressive power. Besides, considering the complex representation property of context and motion nodes, we need to address two hurdles. First, motion nodes mainly encode the pointwise correspondence between an image pair, while context nodes capture the discriminative features for region and shape representations. The representation gap could hinder the effective information propagating of directly overall graph reasoning. Second, motion nodes lack constraints on shape or layout for the potential displacement field, and thus they are unable to yield enough context information for individual graph reasoning. To tackle the issues, we propose an adaptive graph reasoning module to exploit the discriminative representations of shape and region in the global context to guide the learning of motion adjacency matrix with adaptive parameters. Specifically, we propose a graph adapter, which is equipped with dynamic weights from adapter kernel theta VC, and then perform node updating for relation learning with context to motion adaptation. Following the success of prior works, we develop our AG flow based on RAFT model, where flow estimation is performed in a recurrent refinement framework. Here shows our experiments. We compare the proposed approach with state-of-the-art works on two standard optical flow datasets. As shown in the table, our AG flow sets new records of 1.43 EPE on Syntel CleanPass and 2.47 on Final Pass, which significantly surpasses the previous best results by 11.2% and 13.6%, respectively. On Kitty 2015 test set, our approach achieved new state-of-the-art performance of 4.89% in F1 all, outperforming top-ranked methods SCV and RAFT by 20.7% and 4.1%, respectively. Here are some qualitative comparison results. We compare our method with RAFT on the challenging final pass of Syntel and Kitty dataset, which demonstrates that our AG flow is able to fully exploit scene context to effectively assist motion estimation with shape and region constraints, leading to achieving more accurate flow fields with clear motion boundaries. Finally, we conduct extensive experiments for ablation studies to demonstrate the superiority of the proposed method. To sum up, to our knowledge, this is the first work that explicitly exploits scene information to assist in optical flow estimation by using graph techniques. In order to incorporate scene information, we generalize the learning to adapt mechanism from regular grids to the graph domain. Our AG flow sets new records on both Syntel and Kitty benchmarks, outperforming state-of-the-art approaches by a relatively large margin. Please refer to the paper for more details. Thanks for your listening.